how can, information be transferred over the internet safely? Well, you're about to find out in this video, so stay tuned. So before we discuss computers and whatnot, let's talk about, real life analogy. I'll use a real life analogy to first kind of explain this problem. So let's say we have someone called Sally who's trying to send some message or maybe love letter, something like that, to another guy called Ronnie who's waiting to receive that message from Sally. So Sally goes on, gets out a piece of paper, writes something down, and put it in an envelope, whatever, sends it across to Ronnie, and boom! Intercepted by Ivan. So now Ivan, opens it up and reads it, and I don't know what he does with it, but that's not a good thing. So Sally thought, that's not a good method, that's not safe from, Ivan. So Sally decides to, instead of writing the message and just putting it in an envelope, she decides to put the message in a box instead, and then close that box off with a padlock, and then send that entire box to Ronnie. And Sally finds that method's actually quite good because, once the message is in the box, even if Ivan gets hold of the actual box, he couldn't get inside of it because it's locked by a padlock. So that means even if he has the box or whatever, it's still useless to him. However, this does cause an obvious problem, that while Ivan can't open the box, neither will Ronnie because, he doesn't have the key. Only Sally has that key, and then if Sally were to send the key over, that could be intercepted by Ivan, and then you're in trouble because then Ivan could just unlock the box and read the message inside and whatever. So still, that's not really the best method. So then Sally, with that quick wit, decided we need a new method, and it's the following. What she does first is she calls up Ronnie and says, "Hello, it's me. I was wondering if you could just send me an unlocked padlock." And so Ronnie goes on and just sends an unlocked padlock to Sally. And so Sally can wait. She knows it's too late, but eventually the padlock arrives. And what she does is she just gets another box. She puts whatever message she wants to communicate inside of the box, closes the box, and then lock it with that padlock that Ronnie sent to her. So now Sally can just send this box over to Ronnie. And even if Ivan intercepts the box, he couldn't open it because, there's a padlock there. But Ronnie can open it because he has the key, because it was his padlock, so he would have the key to it. So he can just open it, open the box, read whatever message is inside, and, the response to the love message, get married, live happy ever after, whatever, it's no longer our concern. But that's pretty much the system that's going to be used in transmitting data over the computer. That there will be some information that will be kept private by one of the sides, and there will be some information that's going to be shared between the two parties, so that, the information could be encoded and then transmitted and then decrypted by whatever key that is kept by one of the sides. So when you're sending data over the internet, rather than having, Sally and Ronnie, it's going to be instead two computers maybe trying to send data from one another. Instead of their love letter, it might be some kind of secret information that they don't want the world to know. And rather than having physical keys and padlocks, when we're transmitting using computers, these will be replaced by numbers, which will act as keys. Now, the first practical system for encrypting data, and probably the most well-known one, most commonly used one, is called the RSA algorithm. This system was invented by three dudes, Ron Rivest, Adi Shamir, and Leonard Adleman, and coincidentally, their surnames actually spell out RSA. Although maybe that's not really a coincidence, I think they kind of meant that. Now, the RSA algorithm relies on prime numbers, and there are certain properties of prime numbers that makes this system so safe, but I'll get to that later on. Now, this system involves some numbers to be set as public keys, which are, some numbers that are shared between both someone who's trying to send the message and someone who's trying to receive the message, and also private keys, which are kept by the receiving side only, kind of like the key in our analogy from earlier. And so for the actual algorithm of how, these numbers, public and private key, are generated, it goes a bit like this. So first, you have to come up with two prime numbers, P and Q. Then you have to multiply these two prime numbers together, and I'll call that number n. Now I have to find phi of n, which is defined as P minus 1 times Q minus 1. So the two prime numbers minus 1 and multiplying them together, basically. Then the computer have to generate a random number, which I'll call E. So that E is co-prime with phi n. So that, in other words, the only factor between E and phi n is 1. They don't share any other factor. Then the computer has to find another number D. So that E times D divided by phi n will give a remainder of 1. Or in more mathematical terms, ED mod phi n equals 1. And then we're ready to go. As you can see, we have a few numbers here. I'll keep n and E and I'll make these public keys, which means I'll share it with the other guy who's trying to send me the information or whatever. And I'll keep D as my private key, so only I will know, only the computer that's, making up this key will know what D is. And as for P, Q, and phi n, we can just put it right in the trash. So now comes the part where we actually try to send a message. So the receiver of the message, the computer is trying to get the message, will send the data for E and N across to the guy who's trying to send the information. So now the guy who's trying to send the message will have, some string of numbers, which I'll call M. M could just be, whatever message you're trying to send, but convert it into number form, or maybe, I don't know, their credit card details, something, but it's a bunch of numbers. The only important thing is that the value for M, the message, should be lower than N. So then they can go over and code the message, or basically in this formula find what C is. So that C equals to M, the original message, to the power of E, which is one of the numbers from earlier, mod N. In other words, you find what M to the power of E is divided by N, and whatever the remainder of that division is, that's going to be your coded message that you will send over, sending back to the receiver of the message. So now once C gets its way to the other side, the receiver just takes C and put it in another formula to find what M is to get back to M. And to find M, the formula is just going to be M equals C to the power of D mod N. So whatever that coded message is, takes it to the power of D, which is the number that only the receiver of the message, the guy who generated the key, will know, mod N. So C to the power of D, whatever that is, divided by N, and whatever the remainder is, that would just be the number, the code that was trying to be sent over the original message. So right now, using all these letters, it might all sound really confusing. So let me try to make it a bit easier. I'll give a simple example of how the algorithm might work in actual numbers. Okay, so two computers trying to send a message across from each other. So the first step is obviously generation of the public and private key. So the second computer that's trying to receive the message will generate two prime numbers, P and Q. For this case, I'll say P is 5 and Q is 11, just simple numbers for this example. N's simple to find, 5 times 11, 55, and phi n would just be 5 minus 1 times 11 minus 1, so 4 times 10, 40. Now we have to find number for E, so that E is co-prime with phi n. So for this case, I'll say E equals 3. 3 is co-prime with 40 because they don't share any other factors apart from 1, so that works. I'll say E equals 3. And then we have to find a number for D. And for this example, I'll say D equals 27 because that fits the criteria. E times D is 81. 81 divided by phi n, 81 divided by 40 will give a remainder of 1. So it fits the criteria. And then boom, we've got a public and private key. We've got N, which is 55. We've got E, which is 3, and that's going to be sent over to the other computer. And then we also have D, which equal to 27, which will be kept with one computer and will not be shared, with the world. Now, once the other computer gets the numbers for E and N, 3 and 55, they can use this number to encode whatever message they're trying to send. Let's say the message they're trying to send is the number 42. So M equals 42, they can shove the value for M and then the value for E and the value for N into this equation and try to get out a value of C, which is the coded number which is going to be sent back. And what we find is that C equals 3. Just shove that into a calculator or something like that. And then the guy trying to receive the message who produced the key will get this number 3 and be like, okay, let me run this 3 back into the reverse, the decryption algorithm, to find what M is again. So, 3 to the power of 27 mod 55. And that gives, a really long 12-digit number, mod 55, which comes out to 42. So it works. But it's worth mentioning that it's really important that you know this, that in real life you wouldn't be using these, puny 2-digit numbers, small prime numbers. The real world, we use, massive prime numbers, like thousands of bits, big values for P and Q, and then value of N would be massive. And that's why this system is so safe. Because yes, while even if we have the biggest value for P and the biggest value for Q, we can find N fairly quickly. But if we just give a really big value for N, to find two prime numbers that were multiplied to give that value of N, takes quite a long time, even for the best of computers. The process of finding, the two prime numbers that were multiplied together to give what N is, that's still going to take quite some time. And that's why the system's really safe, because of this, little bit of prime numbers, prime factorization problem, that just makes it so long and so tedious, even for the best of computers. So it's only when you find what the P and Q is that you can actually go on and try to decrypt the message as a hacker. And that's going to take a long time, so you couldn't really do that. And this RSA algorithm is one of the major uses of prime numbers in real life. If you say prime numbers are useless, now you've found a use for it. So suck on that. And the fact of using these big numbers, that's such a good way, because they make it so safe. But at the same time, the fact that we have big numbers will also mean decrypting the data might also take quite a long time. Look at our example. Our message is only like 2 digits long in decimal, and the numbers that we have to deal with in the calculations are like 12 digits long. And imagine messages which are like, thousands of maybe bits long. The numbers are going to be massive. And, to decode the information, that's going to take quite some time for, the recipient. And that might be a bit of a drawback of this system. You wouldn't use this RSA algorithm to directly encrypt the actual message you're trying to send. Instead, the actual message that the sender might be trying to send will be encrypted using a different algorithm, a much simpler algorithm which involves what we call session keys. And then this session key is encrypted by the RSA algorithm. And then you would send over both the encrypted message that was encrypted using the session key and the session key, which is encrypted by the RSA algorithm. And then the receiver can use that reverse RSA method thingy that we discussed earlier to get out the session key that was used to decrypt the actual message, and then use that session key to decrypt the message and read out whatever string of numbers that they were trying to send across. And that is the RSA algorithm, one way of sending data over the internet safely. Thank you very much for watching my video, and I will see you again whenever that is. I kind of don't know. After my A-levels are done, I am kind of floating in space and I do not know what's happening anymore.